Good evening, my dear JEE warriors. This is your Captain Shreyas, your physics master teacher on the #1 JEE English channel. Today, we're going to start with one of the most scary topic of all the students and a nightmare for the 12th standard students or the dropper students, because back in the day or 1 year back or 2 years back, you would have studied through this chapter and just gone through it and forgotten about it. So, my dear students, we are starting this chapter right from the scratch so that you understand not just the theory and the concepts, but also apply it with the problem solving and PYQs. So, get ready to learn moment of inertia like never before and some really cool, amazing questions as we move towards the end once we have understood the concepts, mixed questions also. All right. So, moment of inertia, the theorems, and the mixed problems all in today's class with your Captain Shreyas. Yes, your physics teacher. Guys, welcome. Hi, Kirti. Hi, Bijit. Yes, my 9th standard students are also here. Welcome aboard, everyone. And that's my quick introduction. You too let me know about yourself in case you are new to the channel. And if you have forgotten to mark the attendance, please do that right away, right now. By the way, we are doing the entire chapter of rotation in small parts because obviously each topic deserves its time and you need to digest that concept rather than conducting a long session and confusing or making you feel lost. So that is the whole idea. And if you see on the channel, class 11th, lot of syllabus has already been done in case you have not watched it yet. By the way, there is something really cool about today's class. Have you noticed something? Hi Ranjit, hi. Welcome aboard. At least 3 lectures we will need. Yeah, because each lecture will be around 2 hours bare minimum. Oh, first of all, like this video. There is one link below saying ask away. If you just open that, right, it's going to take you to the Vedantu app or the website, and you will be able to watch the exact same class either live or recorded with the help of your best friend, and that is Abe. Yeah, the same lecture, guys, you can watch it with the help of Ved. You will be like, sir, why do I watch it with Ved? What is Ved going to do? Well, if you just go down, I think over here it's little difficult for me on the touch screen. You will see that you can ask doubts even in the live class. That is the best part about it. So it's a little difficult on this touch screen. It doesn't open up so well. Okay. But on your phone or your tablet, it will, yes, give you the option of doubts. Let me know quickly in the chat box if you're able to see Ved in action as you open the same YouTube video, either live or recorded. After the lecture is over, it will make smart notes based on what I'm talking, what I'm writing, and what PDF I provide. That will be also available in the same link. Yes, it will create its own notes with timestamps and screenshots. It is going to be a super powerful lecture, guys. Okay, let's do. Let's do that. Okay. HESE, BJR, yes, there are one-shot marathons also coming up very soon. Stay tuned on the channel. Now, what is this moment of inertia concept? Let me tell you. Okay, I will give you a very laddu example to start with so that you understand what I'm talking about. This is a screwdriver, okay? And I ask you that, listen, you hold it at the center like this girl is holding this stick over here and rotate it. Now, when it is at rest, when you try to rotate it, you will feel some inertia, meaning some resistance by this screwdriver to start rotating. Okay, it will resist. But if you hold it here, imagine at the end, and then try to rotate it like this person is doing, it will feel very different. Which one of the two do you think will be easier? Answer in the chat box. The girl's method where she is holding it at the center, or this guy's method where he's holding it at the end. Which one will be easier to rotate? Answer quickly in the chat box, my dear warriors. Yeah, what do you think the correct answer is? Yeah, if you answered center, absolutely correct. It will be easy because all the particles will be going close to the axis. It will be very simple for you to rotate as compared to holding it at the end. You can try it and then you have to rotate it. Then the circles are big, all the particles are far away and it feels little difficult. This is exactly inertia, but in rotation. See, in translation, the mass of a body, let's say I have some mass and one elephant also has a mass. It's very difficult to start the elephant into motion as compared to pushing Shreyas sir, because elephant has a bigger mass. Same way, the same stick, it has the same mass. Notice, mass is same, but how you are rotating it, whether at the center or at the end, decides how difficult it is for it to rotate, meaning its inertia to rotate. That concept is called the moment of inertia. So the difficulty that you experience while rotating something, right? How easy it is to start rotating or stop rotating, that resistance to the change of state of rotation is explained by the concept of moment of inertia. Okay. Now, this moment of inertia can be calculated easily. I'll show that to you also. But before we go ahead, it's very important to know that the moment of inertia of a body depends on three things. Number one, axis of rotation, which you very well saw. If I hold the same mass at the center, it is different. Whereas if I hold it at the end, it is completely different. So the resistance to change its state is different if the axis changes. Imagine if the mass only changes, same axis is there, but the screwdriver has become heavier, same shape but more dense material. Then it's a very heavy screwdriver. It will be very difficult for me to rotate it. So mass of the body also plays a very important role. The last thing is, let's say I'm holding it at the center. Mass is also same, but let's say the screwdriver becomes longer. Mass is same, axis is also the same, but the screwdriver on both sides becomes longer. Now what will happen if it is a long screwdriver? Then the masses will go in big circle. It will be more difficult for me to turn. Imagine just these two objects. This is also like a small screwdriver or a stick only or a rod. This is a bigger rod. Yeah, imagine both of them had same mass, okay, same axis at the center, but this is a elongated body, whereas this is a smaller body. It is easier to rotate this smaller body as compared to this, because now the masses are moving in big circles. You need more motion, more energy, more difficult to rotate it. So it depends on the distribution of the mass relative to the axis. So if the masses are close to the axis, imagine I rotate the screwdriver like this. Imagine I rotate the screwdriver like this. The masses are so close to the axis when I rotate it in this manner that it hardly feels like I'm rotating it, barely any moment of inertia. But the moment I hold it over here, then the masses are distributed far away and I feel very difficult for it to rotate. So the moment of inertia is very high. How many of you felt moment of inertia? Did you feel moment of inertia? Put a fire emoji or a thumbs up in the chat box. Yeah. Let me know quickly in the chat box. Hi Mutulya, welcome my new student. How many of you felt the concept of moment of inertia right now? Yes. So moment of inertia, it depends on the mass, the axis and the distribution. The moment of inertia is the resistance to change its rotational state, to change its rotational state of motion. Rotational state of motion. Very, very important. Okay. Now let's calculate the moment of inertia and how do I really, figure it out. It's simple. Okay, great. Many of you got it. Yeah, we'll do it as much as possible early, Abhijit. Don't worry. Now just imagine that there is this particular body and it is fixed maybe over here. This is the axis. This is, let's say, the axis of rotation, and it is meant to rotate about this particular axis right over there. Now, every particle will go in circular paths. Every particle on that particular body will go in circular paths. So I'll just show you some of those circles like this, like this. All the particles on that particular body will go in circular paths like this. So if I consider some particles on the body, let's say one particle over here, which is at this distance, it will be moving like this. Some another particle maybe over here at this distance will have a different velocity. Some particle over here on this particular body will be having some completely different velocity. Some particle maybe over here will have a completely different velocity. So if you take velocity of any first particle, it will be angular velocity into distance from the axis. Velocity of the second particle will be angular velocity into distance from that particular axis. So the nth particle will have angular velocity into distance from the axis to that point mass. Omega will be obviously the same. Why is omega same? Why is omega same? Why is omega same? It's the same body. So omega will be the same angular, angular, angular speed, because all the particles will shift, will displace by the same angle. If this moves by 30, this should move by 30, that should move by 30, that should also move by 30. The entire body will rotate by the same angle. So angular speed is same for all. Angular speed is same for all the particles. Is same for all the particles. Keep that in mind. Okay? Clear? Good evening. Nikisha, good evening. All right. Hello, Umar. Now, if I ask you, can you figure out what is the kinetic energy of the body? So, it is rotating. So, the kinetic energy of the rotating body, is nothing but the sum of all kinetic energies, all the kinetic energies of the particles, meaning I have to take half mass 1 v1 square plus half mass 2 v2 square. Like that, I take the last particle's mass mn vn square. Each particle m1, m2, m3, m4, m5, m6, m7, like that. How many over 100,000, 10 lakh, 1 billion particles are there? I take all the atoms, electrons, protons, neutrons, everything, each mass into v square. If I do, I will get the total kinetic energy of this particular body. Great. But I know V1 is omega r, omega r, omega r everywhere. So I will get half m omega square r1 square plus half m, this is m1, sorry, this is m2, omega square r2 square. Like that, I will get half mn omega square rn square. What is common and what is not? I can see, I can take half common, and I can see m1 r1 square plus m2 r2 square, like that, till mn rn square can be put inside the brackets, multiplied by omega square. I can just take it outside the brackets. Now this is the kinetic energy of the rotating body, okay, which is half this summation into angular speed square. This is the moment we take a pause and we start thinking that if we had a mass which was translating, which was basically translating with some velocity, the kinetic energy of translation, we all know in work power energy chapter, It is half mv square. Now, if you have a rotating body like this, then the kinetic energy of rotation will look very much similar. Instead of velocity, we should have angular velocity. Is that right? Instead of this term that you are seeing over here, this term of velocity that you are seeing over here, you will have basically what? Angular velocity. Similar ideology. It is identical in concept, but used in different context. Yeah, this is for translation, this is for rotation. Half is still the same. So I believe instead of mass, whatever will come over here will be having behavior like mass, but used in the context of rotation. But it will be used in the context of rotational motion. So if it is rotating body, whatever term will be there over here will be the concept of mass, but in rotation. And if you compare it right now, you can see that I have half, I have omega square in this derivation. Whatever is inside the bracket is like the mass. And that is exactly what we called the concept of moment of inertia. And the symbol for moment of inertia is basically capital letter I. So I is the moment of inertia, which is equivalent to mass in translation. And you will also see, like in translation, the kinetic energy, if a body is translating, the kinetic energy of that body is half mv square. A rotating body will have a rotational energy, total kinetic energy of half I omega square. Half I omega square. So this I is exactly this term in the brackets. This is basically the rotational mass, rotational mass equivalent, which we call it as the moment of inertia. Moment of inertia, right? That is the moment of inertia. Everybody understood how this formula came? Yeah, super imagining. Awesome. Awesome, awesome. So kinetic energy of rotation is basically half I omega square. And the formula looks very similar to translational energy. Instead of velocity, you have angular velocity. Instead of mass, you have moment of inertia. So now we got the formal definition of moment of inertia, not just what it is or what is it dependent on. We now have a formal definition of moment of inertia, which says that if the body is made up of n number of particles, each having mass m1, m2, m3, and r1, r2, r3 are the distances from the axis of rotation, then the rotational mass equivalent or the moment of inertia is the summation of mr square. So hence, if I have an axis and there are particles m1, m2, m3, m4, m5, m10, like that, 100,000, two particles, doesn't matter. The moment of inertia I is given by take every particle's mass into the distance from the axis. R is not radius, please mind it. Distance from the axis of rotation. Keep adding it till you reach the last mass and the last distance. Often it is also written down as summation. So sigma mi ri square from 1 to n. That is the formula. Everybody clear about this? From this, we can also figure out what should be the unit and the dimension of moment of inertia, kg, and there is meter square. So hence, the unit of moment of inertia, the unit of moment of inertia, and also the dimensions, the dimension of moment of inertia, very easily we can give it off. So the unit of moment of inertia is nothing but kg into meter square. Dimensionally, it is mass raised to 1, length raised to 2, power of time is obviously 0. So that is the dimensional formula. Kg meter square is the unit. of moment of inertia. Clear? Very good. Awesome. Awesome. Great. Now, let us use this concept to figure out the moment of inertia in certain situations. Okay. So, I'm going to give you certain situations. You are going to tell me what is the moment of inertia about the given axis. So, here we are. Basically, it's given to me. There are some masses lying somewhere. Okay. And the distances are also given to me. This is 2 meters. This is 3 meters. This is 4 meters. There is a mass of 1 kilogram. There is a mass of 2 kilogram. And there is a mass of 0.5 kilogram. And there is also one more mass of 5 kilogram over here. So this masses, they are on some frame. The frame is negligible mass. The masses are revolving in different distances from the axis of rotation. Can you figure out what is the moment of inertia of that combined system? That is the question. Like we saw, the formula for moment of inertia is nothing but sigma mi ri square. There are 4 masses or 5 masses, whatever. 1, 2, 3, 4. 4 masses. So 4 terms will come. The first mass is 1 kilo and the distance is 2 meters. So R is 2. So 2 square. That is the first term. Plus second mass is 2 kilo. Distance is 3. Sometimes people write 3 into 2 square. This is a silly mistake which many kids do instead of 2 into 3 square. Then 5 kg mass is at no distance. It is on the axis. So it will become 5 multiplied by 0 square plus it is 0.5 multiplied by 4 square. So what am I going to get? 2 square is basically 4. 3 square is 9. 9 twos are basically 18 plus this is 0 plus 4 square is 16. 16 into 0.5 is basically 8, right? So 8 plus 4 is 12. 12 plus 18 is nothing but 30. So 30 kg meter square is the moment of inertia. 30. How many of you got it? Quickly let me know in the chat box. And I've done 12. From there I started solving. Should I cover syllabus or practice? Jeet Patel, you should definitely do the important chapters like rotation, SHM, because they will be very useful for your upcoming 12th, I mean not board exam, but your JEE 2026. So you better attend this because it is going to come in electromagnetism, AC circuits, light waves, EM waves, the concept of omega, I, everything will be there. So you better do it over here in detail. Okay. Don't leave the 11th standard syllabus. If you are in 9th, you should complete the 11th syllabus somewhere around May, I would say May to April. That is the time where you should be done with your 11th syllabus by next year, right? Okay. Yes, Pritija, I do see your codes on all the videos and they are very unique, very personal and very thoughtful. Thank you so much. I saw the comments and many likes also you have got on those comments. Yeah, right. Okay. That was the formula for this. Great. And this is how you apply it. Very straightforward. The questions on this are pretty much simple. Now, let's say it is given to me that there is a square frame like this. There is a square frame like this. And the side length of it is basically A. The side length of it is basically A. And there are point masses. And there are basically point masses over here. All the masses are identical only. All the masses are identical. M. All of them are M each. The first time, what we are doing is we are rotating, spinning it about this axis. Second time, we are spinning it about this axis. Question is, find the ratio of the moment of inertias in both the scenarios. I'm spinning it like this versus like this. Find the ratio of the moment of inertia in both the scenarios. Okay, so that is the question. So let me write it down over here. The ratio of the moment of inertia. That is the question which has been asked. All right, let's do this first and then we'll shift to the other one. If you notice, in the first scenario, all the masses are at the same distance. This, and this. All the distances are same. And if the side length is A, this is basically A by 2. This is basically A by 2. All the distances are obviously the same from the axis of rotation, and needless to say the mass was originally given that it is same only. So when I try to find the moment of inertia in the first scenario, each mass is m, distance is basically a by 2, it will come basically 4 number of times because there are 4 masses, same mass, same distance. So it will become 4 multiplied by m multiplied by a square divided by 4. A square by 4, 2 square is 4. 4 cancels. I will get this as ma square is the first moment of inertia. Ma square is the first moment of inertia in the first scenario. Now let us talk about this guy. In this scenario, these two masses are already on the axis of rotation. So the particle is on the axis of rotation, there will be no distance only. They will not contribute in the moment of inertia, just like in the previous question over here. Like this 5 kg was on the axis, there was no distance, so it is on the axis, so no contribution in the moment of inertia. So the only two particles that should be counted are these two. And what distance are they at? This and of course this. Now each of the distance will be half of the diagonal length. Okay. Now if you see how much is the diagonal length of a square, it is always a or the side multiplied by root 2. So it is side multiplied by root 2, this is half of the diagonal. So it will be nothing but that particular r will be nothing but the diagonals half, which is a root 2 divided by 2, which is basically a by root 2. So each one of them is at a distance of a by root 2 from the axis of rotation. These two masses are already on the axis, so no contribution there. So in the second scenario, the moment of inertia will be m multiplied by a by root 2, that is the distance square. Like that there are two masses, so I will multiply it 2 times, and the other two masses are on the axis, so 0 and 0 contribution as such. So this will become m a square by 2 multiplied by 2. 2 cancels, it will become m a square. Interesting thing, this is also ma square, this is also ma square. So what does this tell you? What does this tell you? Very coincidental problem. I1 and I2, the ratio is 1:1 because both of them are identical to each other. So 1:1 is the answer. How many of you got it? Now you will be able to calculate any moment of inertia of particles, whether it is triangle, hexagon, square, any random position. You know, just have to add mass into distance square, the summation of it. Yeah, there is sigma. Yes, yes, there is sigma. Sigma means summation. Sigma means instead of putting plus 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 100 times, 200 times, we just put it as a symbol to signify you have to add such identical terms or similar looking terms, m into r square. So in this problem or even the other problem, each mass into distance square, mass, distance square, mass into distance square, mass, no distance square, mass into distance square. So if you add them, you will get the total moment of inertia. Same thing over here also. Each particle was at some distance from the axis. That distance is a by 2 because this is a, so this is a by 2 each. And this will come 4 times because there are 4 masses, so into 4. Here, when I rotate about this axis, so this is going in a circle like that, then this mass and this mass are at a distance of a by root 2 by simple geometry. These two masses being on the axis, they have no distance, so no contribution. That is what it is. And all of these formulas have come just because I started with a general expression taking any random body and rotating it and trying to find its kinetic energy. And I got some summation term. So we defined that summation term by comparing it with the kinetic energy formula, saying let's call that equivalent of mass, let's call this equivalent of mass as a new symbol I, which is moment of inertia. Okay, that's how we created that definition. Is that all clear? Sir, if the mass is on the axis, then we should take it as 0. Yes, because it's a point mass only. Point mass on the axis, no distance. So to rotate that point mass, you will not need any energy. There is no resistance because it is on the axis. When it is away from the axis, then I have to give it some velocity. So I need some energy. So then it is counted in the moment of inertia. Is that okay, Dashwin? Yeah. Yes, yes, Abhijit, I do remember you, man. Of course, almost every class you are there. How can I forget you? Okay. Now, the next part is where the moment of inertia has to be figured out for some irregular shaped body. Let's say this comb. Somebody is trying to rotate this comb and random body it is. There are so many particles that I can't even count. Or this pen, so many particles that I can't even count. So when you have countless, infinite number of particles, we use integration instead of summation. That's also the situation in center of mass chapter. So instead of taking M1, M2, M3, because how many masses will you take? Millions, billions, it is countless. So there you divide it into dm mass, and each dm mass is at some distance r, and therefore instead of summation, you will say the moment of inertia is integration of basically r square into dm. Mr square, Mr square, Mr square summation is now converted into integration. That is the only difference in such a scenario. I is nothing but r square dm. Yeah, that comb is so big. Ooh, because my hair is also so big and my head is also so big. That's why. Okay, let me show you some examples of how we can calculate moment of inertia. The third example is absolutely going to blow your mind. Okay, ready for it? Let's start with a ring. Let's start with a ring. Okay, we have a ring-like structure, not the Ring movie. This is a ring, and this is the axis, let's say. This is basically the axis of rotation. Now, I want to figure out what is the moment of inertia of this particular ring. So, I know I cannot do it directly. I will see that there are many masses on the ring. So, I will take any particular mass on that particular ring. Let's say I call that mass dm, and it is at some distance. But the funny thing is, all the dm masses, all the dm masses are at the same distance. You take any dm mass, all the dm masses are at the same distance of r, which is also the radius of that particular ring. So when I try to integrate by saying integration of r square dm, that r is basically the radius, that dm is over here. R being a constant goes outside the integration. I am just left with dm only because r is the same. All the particles have same r. That is the only reason why it was able to come outside. What is integral dm? If you add all the masses on the ring, you are obviously going to get the entire mass of the ring. So therefore, it is just nothing but mr square. That is the moment of inertia of the ring. Mr square. Very simple derivation. Yeah, I hope this is clear. Now, the second one is nothing but a disk. The second one is nothing but a disk-like structure. So a disk will look something like this, let's say. And let's say this is the axis of rotation. Okay. Each mass is now going to be a different distance. That is the problem. So in order to figure out the moment of inertia of that particular disk, I got an idea. Why not divide it into small rings. Yes, you heard it right. Imagine one ring like this, then another ring slightly bigger than that, like that, and so on and so forth, guys. I will take many such rings. I'll take many such rings and keep on adding their moment of inertia in order to get the total moment of inertia. So is nothing but the total moment of inertia of the disk is the sum of all moment of inertia of the concentric rings of the concentric rings. But how many such rings will be there? Infinite such rings will be there. So it's better to take integration of the moment of inertia of any particular ring. But wait a minute, I already know what is the moment of inertia of any small ring. Basically, it is mr square, mass of the ring into r square. So any such ring over there, if you take any such ring over there, all right, in such a scenario, the mass of it will be nothing but dm, and the radius of such a ring will be small r, but our original disk will have a radius of capital R and a total mass of capital M. That's the complete mass, complete radius. This small r is the arbitrary radius of that arbitrary ring. So therefore, I can say it will be nothing but r square dm, but unfortunately, this is not allowed because this r will keep changing depending on the ring which I am considering. So I'm not allowed to shift that r outside. So I am stuck now. What do I do? Don't get scared. Actually, there is a small thing which we can do. Okay. See, this is a disk, right? So it's a sheet-like object, 2D object. And whenever I have 2D object, what happens, guys? Any 2D object, just imagine any 2D object. The mass is related to how much area I am cutting out. So if I take this much part, that has this much area, this much mass, more area, more mass, because the mass per unit area is the same. So whenever you have 2D objects, you take mass per unit area, 3D objects, mass per unit volume, linear objects, mass per unit length. So over here, the concept that I'm going to use is the mass per unit area. Mass per unit area is going to be the same. Now, if you take the entire mass, it is m, the entire area is pi capital R square. But what about this? The mass is just dm. You might be wondering, sir, what is the area of this? A lot of people are going to write pi small r square. This is a common mistake. No, you got me wrong. It is the area which that line has. It's a ring. There is no mass inside. So how can that inside part's area be counted? Just in fact, open up that ring. Just imagine somebody asks you, just open up that ring and make it flat. It will look something like this. It will look something like this. Okay. It will look something like this. Yeah. You just have to open it up. You just have to open it up. Well. The entire ring's circumference is now the length of this rod, which is going to be 2 pi small r. And if this is r, obviously the thickness of this will be nothing but dr, which is also the thickness of this rod-like element. So that is going to be dr. So now it's like a rectangle, and this area of the rectangle, which is the area marked on the disk on the top, you can visualize. So that much area which it occupies has that dm mass, not the inside part. So therefore, it will just be the area of the rectangle, just the total length multiplied by the upper thickness when you see it from the top. So it is 2 pi r dr. Did you understand why it is not pi small r square, but rather it is 2 pi r dr? So you are opening the ring and you are seeing the area, because the ring's area will be the length multiplied by the thickness of it. That's having very negligible mass, but it is needed. Yeah. Yes, if the density is not uniform, still you will be using integration only. Yes, Abhijit, definitely. Feb is long time, much before that. Okay, Adik, so what was your question, man? I don't know. I couldn't see it. Yeah, great. Now that we understand it, wait a minute. Pi and pi have got cancelled, and I am getting my dm value as, check it out. M is there as it is, divided by r square is also there as it is, multiplied by 2 r dr. So put it over here and we will get most of the answer. So it will be integration of r square multiplied by capital M divided by r square multiplied by 2r dr. Capital M, 2 and r square are constants. So 2m divided by r square is a constant. All you will have is r cube dr. Now the limits will come. This small r will start from the smallest string to the largest string. That means 0 radius to the maximum radius, which is r. So that is where the limits will come, which will be 0 to capital R. And we all know that when we integrate r raised to 3, the integration will be r raised to 4 by 4 using x raised to n formula, and the limits have to be substituted one by one. So 0 to capital R. So I will be left with 2m by r square, and you are going to put r raised to 4 by 4 minus 0 raised to 4 by 4, which is going to make it, guys, r raised to 4 and r square will cancel, 2 and 4 will cancel. So I am going to be left with just mr square divided by 2. That's the moment of inertia of a disk. For a ring, it was mr square. For a disk, it is mr square divided by 2. And you have to remember these geometries, by the way. Like, I have made a table also. I'll show it to you in a bit of a moment, the other geometries as well. So for a ring, it is mr square. For a thin uniform disk, it is mr square by 2. Now there is a funny thing which happens. When you take this ring and you pull it, stretch it along the axis, something like this. In fact, for any two-dimensional figure which is rotating about its axis, what you do is you take that two-dimensional body, and you stretch it. Yes, you stretch it to make it into a three-dimensional body. To make it into a three-dimensional body. If the original moment of inertia is I, which will be some number into m into r square, this body, same mass, but it is elongated, will also have the same moment of inertia. This property is very, very important, where you are stretching a two-dimensional body and it has now become a stretched three-dimensional figure. The moment of inertia formula or the value will not change. There is a simple reason for it. Imagine this was a plate and hypothetically somebody was pulling it, then the mass has not changed. The axis has not changed. Even every mass which will move parallel to the axis. So the distance from the axis has not changed. So mass doesn't change, axis doesn't change, distance from the axis doesn't change. So there is no reason why MOI, moment of inertia, should change. So moment of inertia will remain the same, which is a very useful property. So now you only think, if I take the ring and stretch it, what will it become? It will become a cylinder, but inside there will be nothing. If you take a disk and you pull it along the axis, yes, it will again become a cylinder, but it will be completely full, meaning a solid cylinder. So that's why you will see the formula will be exactly the same. So if a hollow cylinder moment of inertia is being asked or it is rotated, it will be mr square. Whereas if it is a solid cylinder, then the answer will be mr square divided by 2. Is this property clear? This is the stretching property. What is this? This is the stretching property. The mass distribution, why did it not change? Again, I'll just give you a brief idea over here. If this mass was here, over here, that same mass will be elongated over the entire geometry, but the distance from the axis hasn't changed. The distance from the axis has not changed. If this mass was m1, that same mass m1 has now been stretched over like a rod, but the distance from the axis hasn't changed. So that is the reason why none of the three parameters which affect the moment of inertia have changed. So moment of inertia also didn't change. Okay, great, very good. Pritija, I hope you applied for the job where that link was shared, and I think somebody from Vedantu HR team will get back to you. Okay, right. If they find suitable candidates, definitely they'll get back to you. So that was the moment of inertia of a ring, hollow cylinder, disk, and solid cylinder. Now, before going ahead to the next couple of geometries, there is only one more geometry which I will show you, because all other things are again based on pure integration, like a cone, solid, sphere, whatever. And that geometry which I want to discuss is none other than a hollow sphere. What am I talking about? A hollow sphere. Keep that in mind. Hollow sphere. And this is the axis. That's it, guys. This is the axis, and this sphere is basically hollow. Only the shell is there. Inside it is full of air or vacuum, nothing is there inside of it. So that is basically your hollow sphere. And now that is made to rotate, let's say about this particular axis, and we want to figure out what's the moment of inertia. Okay, now first of all, here is what I will do. Observe this carefully. Okay, you take, again, if you do it via integration, no, it is going to take a lot of time, but there is a smart move which H.C. Verma sir has done in his book also. So what happens is, you take any random mass anywhere, okay, anywhere on the sphere surface, any mass. Let's say that mass is dm. It will rotate about this particular axis with this particular distance as the radius, isn't it? With this particular distance as the radius. Now that radius can be written down in terms of coordinates, provided I choose my coordinates wisely. Okay, this is my x-axis and this is my y-axis. Now I want you to visualize this particular geometry, that dm mass is actually going to be in three-dimensional figure. It's actually going to be a three-dimensional figure. I want you to visualize it. Yeah. So this dm is on the surface, and when it rotates, then it is at some distance from the axis. You can visualize this in 3D. Okay. And that distance is basically r. Now, guess what that particular r will be. Guess what that particular r will be if you visualize that in 3 dimension. Just think about it. Just imagine that to be in 3 dimension. Okay, this could be the distance. This mass can be anywhere, by the way. It could be here also. Okay, if you are getting confused, okay, and you are thinking, sir, that it will be the z coordinate. No, no, no. Let me be very, very clear, guys. That particular mass can be anywhere around. So just visualize and feel what might be that r exactly equal to. If you think carefully, then you will realize that that particular mass, if you see it from the top view, okay, if you see it from the, what did I say, top view, if you see it from the top view, then probably this is what you're going to see. This dm mass is at r distance over here like this, and This is going to be your x-axis. This is going to be your z-axis. Observe carefully. This is your x-axis. This is your z-axis. This is x. This is z. I'm spinning it about the y-axis. Are you able to visualize? Now think and tell me what is r. Yes, that dm mass will have some x and y coordinate. So this much distance will be the z coordinate, and this much distance will be the x coordinate. Isn't it obvious that r will be basically nothing but x square plus z square, the whole thing under the root? R will be nothing but z coordinate and x coordinate square under the root using Pythagoras theorem. How many of you see this? Okay. Oh yes, Azad, I'm pretty sure you too will look different. Just look at your Aadhaar photo. I'm pretty sure you will also find a lot of difference between you and um, whatever you are right now. I'm pretty sure it must be more for you, especially if you are in your teenagers, right? I'm though still quite old. Yeah, awesome, awesome. All right. So this is how you are going to get any particle's distance from the axis of rotation. So as I'm rotating about the z-axis, the moment of inertia, which is going to be r square dm from the z-axis. So r is x square plus z square. So it will be x square plus z square into dm. Okay, so that is basically Iz. Now, if I were to rotate it about x or z axis by same logic, so I can say similarly, 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 if I were to rotate it about Ix or x axis, or if I were to rotate it about the y axis, what will the formula look like? When z is there, x and z, sorry, it was not z axis, it was y axis, my bad. So sorry guys, I mistook it, my bad. The vertical axis was not z, it was y axis. I'll reframe it. This was the y axis. Then we will spin it about the z axis, and then of course the x axis. My bad. Oh. So when I was spinning it about our y axis, then z and x coordinates came. So if I was spinning it about z axis, then which coordinates will come? X coordinate will come and y coordinate will come. Is that right? And similarly, if I were to spin it about my x axis, then which coordinates will come? Then obviously y coordinate will come and z coordinate will come over here. How many of you understood this logic? How many of you understood this logic similarly? So first I said, if I'm rotating about the y-axis, each dm mass will go in circles like this, okay, which will go in circles like this around that particular axis. So the radius of that circle will be given by x square plus z square under the root, and it is very easy to visualize it when I see it from the top, that this mass will be at some distance having z and x coordinate. So same logic I can apply to other axes as well. Now what happens is, we know it's a sphere, uniform, every side is same, every axis is same. So technically Iy, Iz, Ix are actually equal. So actually speaking, Iy is I, Iz is also I, Ix is also I. So if I add all of them, if I add all of them, if I add all of them on the left hand side and the right hand side, I will have Ix plus Iy plus Iz, which is actually I plus I plus I, which is nothing but 3 times of I. And on the right hand side, we will have integration of x square plus z square dm plus integration of, oh, so when integration is there, I can just write it as a common integration, and dm is also common. So might as well write it as x square plus z square plus x square plus y square plus z square, whole thing into dm. One common integration. This, everything has dm common. So x is 2 times, y is 2 times, z is also 2 times. So 2 times integration of x square plus y square plus z square, the whole thing into dm. Now the funny part is this x square plus y square plus z square for any three-dimensional sphere is actually the radius of the sphere, is actually the radius of that particular sphere of having mass m. So by three-dimensional geometry concept, this is nothing but r square and dm is there. All right. Next step, guys. Next step over here. I think I will just take this thing on this side. Yep. So we have on the left hand side 3 times of I is equal to 3 times of I is equal to this capital R is the radius of that sphere. It is a constant, so it can come outside. So 2 times of R square integration of dm. Integration of dm is nothing but the total mass. Therefore, we have got the moment of inertia as 2 divided by 3 mr square. So actually we never integrated as such. If you notice, we have just played around with the problem and we have used similarity or symmetry property and just added all the three axis moment of inertia to get the actual moment of inertia. So that is what you will see is the moment of inertia of a hollow sphere 2/3 mr square. For a solid sphere, you need to integrate it properly using disks, and it is 2 by 5 mr square. Remember this. Okay. Okay. Sir, for please sir for ellipse because it has two radius, one major minor axis for axis of usual. It will be usually given to you that which axis is there, but usually it should be rotated about the minor axis, not the major axis. Usually, but there is no hard and fast rule, so it should actually be given. Okay. So I hope you loved this derivation. How many of you loved this derivation? And if you have loved this derivation without integration, smash the like button right away right now and subscribe to the Vedantu JEE English channel. Yeah, do it because that is what this channel and me is all about. I give you quality content which is very rare on YouTube. Okay, great, perfect. Now same logic you can also use for hollow cone and solid cone. Anybody remembers the values? Solid cone and hollow cone. Yes, for hollow cone and solid cone, what is the formula? For hollow cone, the formula for moment of inertia is nothing but half mass into radius square. Height has no role to play. For a solid cone, it is 3 by 10 mr square. It is very rare you will get cone problems, but I am giving it to you. Mr square by 2 for hollow, and for solid, it is 3 by 10 mr square. As simple as that. For solid sphere, 2 by 5 mr square and 2 by 3 for hollow sphere. Similarly, for ring or hollow cylinder, mr square. For solid cylinder and disk, it is mr square by 2. These are the major geometries. And one last geometry is of the rod. So if you have a rod like this pen over here and you're spinning it about the center, not at the end like this. No, that is not what I'm saying. At the center, if you spin it, then the moment of inertia is just mass of the rod into length square, entire length square, divided by 12. Remember that number 12 is very important. Okay, everybody clear? Perfecto. Arthamaindindi? Yes. Everyone. Solunga. Yes. Understand Panunga? Everyone, come on. Clear? Okay. All these formulas, by heart it. By heart it now. ML square by 12 is for rod about the center. Everything is central axis only. hollow cone mr square by 2, solid cone 3 by 3 by 10 mr square, solid sphere 2 by 5 mr square, hollow sphere 2 by 3 mr square, disc or solid cylinder mr square by 2, hollow cylinder or ring is just mr square. These are all the formulas that you're going to need. Great. Now we'll start with a question actually, but before that, one small concept of radius of gyration, then we'll go ahead. Yeah. Oh, I was just asking, did you guys understand in Telugu and or Tamil? Okay. Don't get scared, Pritija. All right. Now, last concept before we go ahead to the theorems and addition subtraction problems, radius of gyration. So, say for example, we have some random body over here who is rotated about some axis. That body has some mass, some dimensions, whatever. I want to condense that body into a singular mass or a ring, maybe into a point mass, let's say, into that same point mass, such that this body has the same moment of inertia as that of this body. Then the distance at which I should place this mass, when I complete that mass into a single point, how far I should place that mass is called K, which is radius of gyration. So, what is the radius of gyration? It is the distance from the axis where the entire mass of the body is concentrated for the same moment of inertia. For getting the same moment of inertia. So our original body might have some moment of inertia I. The moment of inertia of that point mass is just going to be mk square. So from this we will get k is equal to root of the moment of inertia of that particular body divided by the mass. That's it. As simple as that. That is how you can calculate the radius of gyration. Mass of the body into radius gyration square is the total moment of inertia of the body. If I place the mass far away, then inertia will change. Maybe it will not be the same. If it is too close, it might be different. So that apt distance which will behave like the body is the moment radius of gyration. Okay. Yes. Yes, Pritija, we are definitely looking for people who can help us with the content always. And definitely, if you have applied, we'll look into it. Okay. Don't worry. Now, having said that, let's do some questions based on this. Can you figure out the radius of gyration for solid and hollow sphere? For solid and hollow spheres. Let's figure it out. Starting off with solid first. Okay, let's start with solid sphere first. So moment of inertia of solid sphere should be m into k square. Moment of inertia of a solid sphere is 2 by 5 mr square. So this will be m into k square. Cancels. So basically we will get k square is equal to r square multiplied by 2 by 5. So therefore k will be r under root of 2 by 5. So that is the radius of gyration of a solid sphere, r under root 2 by 5. Now let's do for hollow. So the moment of inertia of a hollow sphere will be m into k square. For a hollow sphere, we just calculated it is 2 by 3 mr square. So that will be m into k square. Cancels. So k square will be 2 by 3 times of r square. So taking square roots, it will be r under root of 2 by 3. That is the answer. Very clear? Simple? Okay. Let's go to the next question on your screen. Here it is. If the radius of gyration, if the radius of gyration is 3 meters for a body whose moment of inertia is 24 kg meter square, find its mass. Find its mass. That's the question. Let's solve this. There is a body having a moment of inertia of 24 and the radius of gyration is 3 meters. We understand the formula of moment of inertia and radius of gyration is I is equal to mass of the body into radius of gyration square. The moment of inertia is given to be 24, mass is unknown, radius of gyration is 3, so 3 square. Therefore, 24 is equal to 9 times of m. Therefore, m will be 24 divided by 9. Well, 24 goes with 3, 8 times, 9 goes with 3, 3 times. So, mass is 8 by 3 kgs. That is the answer. 8 by 3 kgs. Is that clear, everyone? Pakka? Understood? That is how you use moment of inertia and radius of gyration whenever needed. All right. Now, let's see if we can figure this out. Next one on your screen, here it is. If a cone, actually, if a hollow cone of 4 kgs mass and 2 meter radius, 3 meter height is spinning at 10 radians per second, find the rotational kinetic energy. Find the rotational kinetic energy of that particular cone. So we have basically a cone and it is spinning about this particular axis. Find the rotational kinetic energy. We all know to find the rotational kinetic energy, we need the moment of inertia of that cone. Now, the standard formula for moment of inertia of a what kind of cone? Hollow cone is mr square divided by 2. That's the formula. In case you have forgotten it, use this chart for now. Mr square by 2 and 3 by 10 mr square is for solid cone. So we are going to use hollow cone formula, which is mr square by 2. And what is the rotational kinetic energy formula? I started my lecture only with that, saying that in order to calculate the kinetic energy of a rotating body, we derived this concept and we said that the term mr square summation is I and kinetic energy is half I omega square, just like half mv square. So we just have to use half I omega square formula. That's it, nothing else. So let's use that and see what do we get. So the kinetic energy of rotation, what is it going to be? It is going to be half I of the hollow cone into omega square, which will be half into moment of inertia is itself mr square by 2. So mr square by 2 multiplied by omega square. So this will be half. Mass is how much? 4 kilos. Radius is how much? 2 meters. So 2 square divided by 2 multiplied by omega is how much? 10. So 10 square. 2 square cancels. 4 into 10 square, which is 4 into 100, which is 400 joules is the answer. Yeah. Is that clear, everyone? I think I had just made a video on calorimetry just a couple of days back in a short series. You should just check it out. We had done that right over here. Heat and temperature. Okay, you can just check this lecture out. It's a beautiful class on heat, temperature scales, thermal expansion, heat capacities, and calorimeter. Okay, so just check that lecture. I think it will be better. Yashvik, we are doing this series, and a lot of students wanted us to do 11th standard portions in detail and not in a hurried manner. Number two, 12 standard marathons are coming specifically. Okay, wait for it. Yeah, all right. Yes. KG Tech for 2026 marathons are starting next week. All right. Cool. Okay. Let's do this particular question, which was asked in JEE 2021. Okay. Ready for it? Let's see. The diagram is showing two discs of radius capital R and small r. Capital R and small r. They are placed one over the other. The mass per area is same. Mass is not same. Mass per area. Their areas are different. The discs are different. So different masses might be there. What is the ratio of the moment of inertia of the bigger disk about an axis which is perpendicular to the plane? That means your standard axis, central axis, which is perpendicular to the disk, to the smaller one, and to the moment of inertia of the smaller disk around one of its diameters lying on its plane, given m is the mass of the larger disk. Moment of inertia is mi stands for moment of inertia. Actually, we need one more theorem for solving this particular question, okay, because diametrical axis is given. So we'll actually come back to this particular question in a bit, and then we will try and solve it. Okay, but yeah, this is a good question. We'll come back to it. All right. So the theorem that we'll need is actually perpendicular axis theorem, and then we will see what it is. Now, when we had standard axis, we know the formulas of moment of inertia, but the problem happens when the axes are shifted or they are in a different direction. Imagine the rod's axis was not here but here. Imagine the axis was not here but somewhere else. That means the sphere is here and it is rotating like this. The axis is somewhere outside or maybe inside only but at a different place. Or maybe here the ring is rotated about its diameter or the disk is rotated about the tangent. So the disk is going like this. So in all these scenarios, we cannot use these formulas. We have to transform the axis. So the transformation formulas are very useful. So there are only two transformation formulas or theorems, you can call it. First is perpendicular. Next one is parallel. Now, what does the perpendicular axis theorem say? First of all, this theorem is only valid, is only for two-dimensional laminar objects, laminar bodies or objects. That means ring, disc, plate, that kind. The moment it becomes something else, it is not valid. Got it? Like a sphere, hollow sphere, cone, even a cylinder, you cannot use it. Okay? Great. Now, what happens is, if you are spinning it about this axis, which is perpendicular to the plane of the figure, versus you're spinning it about two different axes which are in the plane of the figure and also perpendicular, these three moment of inertias are actually related. How they are related? Let me show it to you. It's straightforward. Imagine if I were to spin this particular body about the x-axis. If I were to spin the moment of spin it about the x-axis, and if you take any mass, that mass will go in a circular path like this, with this axis being the central axis for that circle or the circular motion, and the radius of that particle on that particular lamina will be exactly the y coordinate. Think about it. When any mass will revolve with the x-axis, then the radius of that circle will be the y coordinate. How many of you got this concept clearly? Why it is the y coordinate? Just visualize. You take any particle here, it will rotate like this. Yeah. this radius will be exactly the y coordinate. So this will be integral y square dm. Now, if I rotate this body about the y-axis, if I rotate it about the y-axis, guess what? The same particle will now revolve like this, and this will be the radius, which will be x coordinate, So it will be integral x square dm. Now what we will do, we will just add both of them. So adding both of them, let's see what do we get. Here we will have ix plus iy will be integral x square plus y square common dm. Now the funny thing is that x square and y square, if you use Pythagoras theorem, this is x, this is y, this is right angle, the hypotenuse is r, which is the distance from the z-axis. So x square plus y square is actually r square. That's it. This is very, very critical, guys, over here. As you can see, okay, this is basically your x, this is your y, this is perpendicular, this is basically r. So r is basically y square plus x square. So that's why it is r square over there. But what is this formula looking like? This is looking like the moment of inertia. When you spin it about the z-axis, then this particle will go in a circle whose radius is this r. So this is actually the moment of inertia about the z-axis. So what have you got? Moment of inertia about the axes which are in the plane, the sum of it is the moment of inertia about an axis perpendicular to the plane. And it is only and only valid for two-dimensional or laminar bodies. Because if it is not laminar, then this derivation will not hold true, because this exactly won't be y square. This also won't be x square, because when you rotate it like this, then each particle would, if it is a three-dimensional object, each particle will not be at y coordinate distance for the radius. It might be something else only. So that is why it is only valid for two-dimensional bodies. Okay. All right. Aditi Krishna, if you are little late 14 minutes back and should be by heart the moment of inertia equation, or we should study the integration steps, allow it, but the time is limited. Aditi, if you are a 2026 student, by heart. If you are a 2027 student, please look at the steps. Okay? Yeah. I'm pretty sure. Because physics and apply JEE in 2020. Thank you. I'm so glad, William Joshua, you're loving the classes and keep studying like this. So, we can see some questions based on that. Imagine there is this disk over here. Okay, imagine there is this disk over here, and let's say we want to figure out the moment of inertia about this axis. This is the moment of inertia about the diameter. I want to figure that out. So what we will do is, I do not know this moment of inertia. What I know right now is this moment of inertia. If it rotates like this, perpendicular to the plane of the figure, this moment of inertia I definitely know, and that is mr square divided by 2. Now this axis is perpendicular, but for perpendicular axis theorem we need 3 axes. So we identify the third axis, which is in that plane only, and that is also a diameter. So even that will have I as the moment of inertia. So whether you rotate it like this, or whether you rotate it like this, like this or like this, disk is the same, symmetrical. So moment of inertia will be same. Now two moment of inertias are in the plane. One of them is perpendicular. So using perpendicular axis theorem, perpendicular axis theorem, we can easily see I plus I, which is going to be 2 times of I, will be the moment of inertia along the perpendicular direction, which is mr square by 2. So from this, we get the moment of inertia is mr square divided by 4 along the diameter. Is this concept clear? How we applied the perpendicular axis theorem? We artificially created one more axis to just apply perpendicular axis theorem because it needs 3 mutually perpendicular directions to apply it properly. And then we added those moment of inertias to get the perpendicular directions moment of inertia, which was already known. I didn't have to find that. Rather, I had to find this solving. Now, if I go back to this particular question, it becomes easy. See, in the first scenario, the ratio of moment of inertia of the bigger disk. So for the bigger disk, the axis is perpendicular to the plane of the disk and passing through the center. So the first moment of inertia is simply mr square by 2, meaning that disk is like this and the axis is over here perpendicular to the plane. That is the first scenario. Now the second scenario is moment of inertia of the smaller disk along its diameters in its plane. That means the smaller disk's moment of inertia has to be found about this axis. So that I2 will be that particular mass. I don't know how much it is, but it will be r square divided by, when you rotate it about the diameter, what did we just figure out? About the diameter, it came out to be mr square by 4. mr square by 4. So using that concept, it will be mr raised to 2 divided by 4. Is this much part clear? How did we get it? Using perpendicular axis theorem. Using perpendicular axis theorem. Okay, very good. Awesome. No, this is not for a ring. This is for a disk that we are doing. Okay, it is clearly mentioned this is disk. And the problem that we solved also was for a disk only. Okay, mr square by 2 was for a disk, if you remember. Okay, now the question is find the ratio of both of them. So let's do that. So if you notice, I1 divided by I2 will be nothing but, okay, on the top, we will have mr square divided by 2, and at the bottom, we will have small m r square divided by 4. But do not be foolish to cancel m. That is the common mistake which many kids did in the year 2021. It is clearly mentioned mass per unit area is same. Meaning, if you ask me the mass of the bigger disk, and divided by the area, which is pi into r square, that will be also equal to mass of the smaller disk upon its area, which is pi r square. So, technically speaking, from here, what I'm getting is m is over here, r square will go on the top, and I will get small m over here, and this small r square will remain over here. Capital M by m is capital R square by R square, because why was I able to tell this? Why was I able to tell this? Because it has same mass per unit area. Same mass per unit area. Mass per unit area is the same. Okay. So instead of m by m, I can also put r square by small r square. R square by small r square. Is that absolutely clear? Instead of capital M by small m, I can put capital R square by small r square. Rest of the things still remain, like this one r square divided by 4 is still remaining. And of course, on the top, that capital R square by 2 is also remaining. So a lot of things are going to get cancelled, maybe. Like I can see 2 and 4, 1 by 2 will remain, and we will be left with r raised to 4 divided by small r raised to 4. This 1 by 2 will remain. Therefore, it will become 2 times r raised to 4 by small r raised to 4. 2 times r raised to 4 by small r raised to 4, which is option number D, of course. Yeah, D for IT Delhi. How many of you loved this question, guys? Isn't it a beautiful, beautiful question? Yeah, yeah. I hope this is absolutely clear. How many questions should I solve so that a chapter is done? As long as you get, you know, one easy or two, three easy, two, three medium, and one hard question in a line, correct, with maybe some hints, but it's okay. As long as you get that confidence, you should keep doing questions. So there is no number for it. I hope, Abhijit, that is absolutely clear. Yeah. Charan YT only. Sir, is your live fun streaming for only 16 people? Charan, also I have a question. Is your life also fun getting 90 percentile or 85 percentile only? Or are you getting 99 percentile and having fun? I would love to know that. All right. Okay. So let's move ahead to one more amazing question coming up on your screen. Now, this is also really, really killer, guys. Observe this carefully. So let's say we take a rod. Let's say we take a rod and the mass is m, and this is having some length L. Okay, and I'm spinning it about its central axis. I'm spinning it about its central axis. Now I stretch that rod so that it becomes like a sheet. What does it become? Like a sheet. Doesn't matter how wide or whatever, but it has now become a sheet-like figure like this. We know by the stretching property, whenever I stretch a two-dimensional, one-dimensional object and I pull it along the axis, the formula for moment of inertia should not change. So whether it is this rod or whether it is this rectangle of how much ever breadth, the moment of inertia will be ml square divided by 12, as long as I'm spinning it about this axis. So it's a plate and I'm spinning it from the center like that. Are you able to visualize it? Everyone? Okay. Awesome. 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 Okay. Perfect. Hi, everyone. Hi, hello. Welcome. Now, imagine I took that same plate. Imagine I took that same plate. Imagine I took that same plate, and what I did this time was, instead of spinning it about its length, I am taking the breadth side of it, let's say B, and I'm showing an axis over here, and I'm spinning it about this particular axis. By the same logic, if I spin it this way, what should be the moment of inertia? So when I was spinning it about its length, then it was ml square by 12. When I spin it like this, it should be mb square divided by 12, isn't it? It should be mb square by 12. Okay. Now I will combine both of them. Look at this. This is our plate. Oops. This is our plate. This is something which no teacher would have told you. I'm pretty sure it's one of the most craziest concept to visualize. Many people don't even reach till here. And this was also asked in different ways in JEE. Now I'm just showing that same plate in basically 3-dimension. Okay, 3-dimension. So this is, let's say, the length. Let's say this is the breadth. So if I spin it about this axis, or if I spin it about this axis, I know what is the moment of inertia. So about this axis, it is mb square divided by 12. About this axis, I know it is nothing but ml square divided by 12. Both axes are perpendicular and this is a two-dimensional figure. I have a brilliant idea now. How about drawing a perpendicular axis like this and trying to spin it? Perpendicular axis like this and trying to spin it. Yes, You might have expected what should be the moment of inertia use perpendicular axis theorem. It will be nothing but ml square plus b square whole thing divided by 12. Isn't it? ml square plus b square. Yeah, ml square plus b square, the whole thing divided by 12. Yes, isn't it using perpendicular axis theorem? Loved it. So from a rod, I pulled it ml square by 12. If I can do it about the length, same thing should be valid for breadth. Both of them are perpendicular. So the perpendicular to the plane of the plate or sheet will be ml square plus 12, b square by 12. But the interesting part is yet to come. Yeah. Now what I will do is, some of you might have guessed very cleverly what Shreyas sir is going to do if you have been attending my classes long enough. Yeah, Shreyas sir is going to make a cuboid. I'm going to stretch it. I'm just going to stretch it. It's going to be fantastic, guys. Look at this geometry. Isn't it insane? Believe me, no matter what the height is, doesn't really matter. The formula for the moment of inertia for this cuboid is still the same. Yeah, it is the same. No matter how much you stretch, by stretching property, the formula should be the same. So same moment of inertia. Crazy, right? How many of you loved this question? Using perpendicular axis theorem only and stretching property. Smash the like button in case you have forgotten to do so. Many people forget it. Just from a rod, I have derived the moment of inertia of a cuboid. Just from a single rod, I have derived the moment of inertia of a cuboid. It's crazy. Yes, moment of inertia does depend on the shape of the object. I have told this before. The distribution of the masses, definitely it does depend. Sir, then this is same as the case one, not really sure. So see it part by part. For a rod, for a rod, for a rod, the moment of inertia about this central axis was ml square by 12. There is a property by which you can stretch. The formula remains the same because distribution, mass, axis, everything is the same. So I've just used that property over here. So I took the rod and I stretched it. So as long as my plate is rotating about this particular axis, the moment of inertia will still be ml square by 12 like a rod. Now, instead of this axis, if I rotate it about this axis, it will be mb square by 12. So this plate, when rotated about this axis, is mb square by 12. And if I rotate it about this axis, it is ml square by 12. Both of these axes are perpendicular. So the third axis moment of inertia should be mb square by 12 plus ml square by 12, which is perpendicular to the plane of the sheet. Okay, which is perpendicular to the plane of the sheet. So the first axis was, think of it like the length axis was here. This is the screwdriver, which is that axis like this. Okay, imagine this. Sorry, guys. Yeah, like this. This was the axis. Second time, this was the axis like this. So now I'm visualizing it this way. I'm visualizing it this way. First axis, second axis, third axis. The pink one is perpendicular. So that will be using perpendicular axis theorem. Now this sheet-like figure, I'm stretching it to make it into a box, which is a cuboid. Is that now clear? Yeah, very good. Yes, Harshul, I hope this is clear. Yeah, amazing. So now that we have understood perpendicular axis theorem, the only thing left, and some problems of mixed nature, of course. Yeah. Shapeless object, Ragul, if it is a shapeless, you should know the equation of that shape. What do you mean by shapeless? Shapeless means something will be there. Some equation of that diagram will be there. If you know the equation, you can do it. So, or else, if it is not given, then you have to take out every single particle and know its distance. So, you should know the function or the shape or the equation, the graph, something you should know. How can you say that I don't know anything and I want to find the moment of inertia? So that is a completely different story then. Yeah. Hi, Pavitra. Good evening. Now comes the parallel axis theorem, where you have an axis which is passing through the center of mass and you shift it to another parallel axis and you figure out what is the new moment of inertia. But the best part, it is not just for 2 dimension, even for 3D, well, not 4D, any kind of geometry you can use it. So this is valid for all the geometries. So this is valid for 2D and 3 dimension, basically everything. So what happens is, if you know the center of mass and the moment of inertia about it, I want to figure out what is the new moment of inertia about a parallel axis. This is the parallel axis. This was the axis through the center of mass. This was axis through the center of mass. What you need is one last thing, is how much are you shifting the axis by? This is parallel to this. So what is the distance by which you are keeping that distance between those two parallel lines and the mass of the body? Just add md square to the center of mass, moment of inertia, you will get the new moment of inertia. It's that simple. If you know the moment of inertia about central axis plus m, mass of the body, into the shift square, that is the parallel axis moment of inertia. So it's time to block this as well. Very crucial. This also tells me one very interesting thing about that body. That imagine if there was some kind of body over here, some kind of random body over here, and I know that the center of mass is, let's say, over here, and I have multiple axes. This is passing through the center of mass. This is passing through the center of mass, and there are multiple other axes. Maybe there is an axis like this. Maybe there is an axis like this. Maybe there is an axis like this. Maybe there is an axis over here. God, so many different axes are possible. All these axes are at different distances. No matter where the axes are, except for the center of mass, this D will always be there. Like you can see over here very clearly. Okay, this is basically the shift. In this scenario, I'm shifting it by this much amount. In this scenario, I'm shifting it by this much amount. In this particular scenario, I'm shifting it by this much amount. So the term after center of mass is always there. So the parallel axis moment of inertia will be ICOM plus some quantity. That means of all the parallel axes that are available to me, the least moment of inertia will be for this axis. So ICOM is the least of all the parallel axes for that particular body. No matter where you go, there is always this extra term. Only when the axis is through the center of mass, this term will vanish. So it will be the least. Else, this term will increase the moment of inertia. Is this absolutely clear? This was a statement-based question which was asked once in JEE mains. Yeah. Okay. I hope this is absolutely clear. Sir, 1 hour to go for the registration to end. What should I do? Like, I don't feel like that confident to register. I hope to write the April attempt. My name is Arav. What should I do, sir? I didn't register. Ignite, register. Trust me. If you don't register, you will regret it. But, if you register, you always have that chance of not giving it. I mean, you always have that option of not giving it. But if you don't register, you don't have the option to give it, even if you prepare a little bit. I feel in the next 1-2 months, we can still do at least something, if not everything. And that something should be good enough to get some percentile. Okay, worst come worst will happen. You'll get 0 percentile, no? Nothing worse. You can't get less than 0. Now you have 2 months. Many people are thinking just like you. I will not study or I will not get time. Many people will give up also. But maybe if you just push yourself a little bit, maybe instead of 0 percentile, at least you will get 50 or 60 or 70 or 80. So for April attempt, you won't be starting from 0 percentile, isn't it? At least you will be starting from 50, 60 or 70. It's better than starting from 0. And if you don't give it now, what guarantee you will have that confidence to give it in April? Because then you have to fill in 100 percentile gap. Just maybe you might get 80 percentile or 90 percentile even now. And then you barely have to cover up a little bit more and maybe you will do better. So please register. Okay. Right. Okay. Perfect. Let me show you some questions based on this as well. One of the most common question being, let's say, for a ring or something, and the axis is not the central one, it is like this, passing through one of the end. And the question is, what is the moment of inertia about this particular end, assuming this is a ring. Assuming this is a ring, okay? This is one type of question. And then another type of common question, there is a rod. This is a rod. And the axis that I'm rotating it about is over here. Usually, we rotate it about the center of mass, like this. Usually, we rotate it like this. So that is not the axis, but it is this one. Okay, these two questions, let's try and solve it. Okay, one by one. Now, usually this green line will not be given to you, of course. Okay, anyways, we'll do it. So first of all, this is the parallel axis, as we can see. This is the parallel axis. The green one is obviously passing through the center of mass, and ICOM, I know already it is mr square. Next thing that we should know is how much am I shifting it by? I am shifting it exactly by the radius. So plus m into shift, which is r square, will come. That will give me this parallel moment of inertia, isn't it? So this is just going to be 2mr square. That's the answer. 2mr square. Very straightforward. Everybody got it? 2mr square. Yeah. Always any axis passing through the center of mass? Yes. So through the center of mass, there could be many other axes, like, there can be one axis like this, one axis like this, but ICOM represents an axis passing through the center of mass. Through the center of mass, you can have infinite axes passing through it. Okay, through a center of mass, you can have infinite axes. We are considering one such axis passing through the center of mass. Plus mass into the shift square is the new parallel axis moment of inertia. All right. Let's do it for the rod in a very similar fashion. Obviously, this is the center of mass, and the moment of inertia about center of mass for a rod is ml square by 12. I am shifting it this much, and this shift is obviously length by 2. So plus m into L by 2 whole square. That will give me the moment of inertia of the rod about this end, which is also the parallel axis, parallel to the center of mass. So let's see, what do we get? ml square by 12 plus ml square by 4. So this will be ml square plus 3ml, sorry, not 3, 3 only, 3ml square divided by 12, which is 4ml square by 12. 4, 12 goes 3 times. So it will become ml square divided by 3. So that is the moment of inertia about the end of the rod. So for the center, it is by 12. For the end, it is ml square by 3. Is that clear? So we have used parallel axis theorem in all the situations. All right, let's do more questions. Coming up on your screen here is the JEE question up for all of you. The moment of inertia of a circular ring of mass m and diameter r about a tangential axis lying in the plane of the ring. Why do I feel that it is none of the problems that we solved before? In fact, a combination of problems that we have solved. Let's visualize what is being asked. So we have to find the moment of inertia of a circular ring. Okay, let me draw the ring. This is that ring. Okay, mass m and diameter is r. Oh, so usually radius is given as r. Here diameter is given as r. So diameter r is 2 times of radius, and let me take the radius as capital R. So capital R is my radius, small r is my diameter. So this is first of all a confusing question. Silly mistake chances are very high. So the paper setter in 2025 has played with the minds, anxiety, the nervousness of the kids. Many kids did not even read the word diameter. They immediately think R means radius, but here diameter is R. Okay, symbolically, not otherwise diameter can't be radius. It is symbolically R. Okay. You have to find about a tangential axis. So draw a tangent to the ring in the plane of the ring. So let's draw a tangent to the ring first of all. This is the tangent drawn to the ring in the plane of the ring. Remember, the plane of the ring will be like this. This is that plane of that ring. Okay. Anyways, in order to find this out, I feel we might need to find the moment of inertia about this axis, which is definitely passing through the center of mass. And this is my moment of inertia about the tangential axis. Only then I can shift and find it out. So the moment of inertia about the tangential axis is, if you know the moment of inertia about the center of mass, plus how much am I shifting it by? It's very obvious. How much is that particular shift? It is the radius. It is the radius plus m into r square. But the problem is I do not know how much is this. Do not say mr square. Mr square is about a completely different axis. In fact, it is about this axis right over here, which is passing perpendicular to the plane of the figure. Oh, so this I perpendicular I know is mr square. Through this, can I find this axis? I think so. I'll tell you why. If you just draw one more diameter, this diameter and this diameter are same, and using perpendicular axis theorem, using which theorem? Using perpendicular axis theorem. Perpendicular axis theorem. This axis and this axis both are diametrical. Moment of inertia about the diameter plus moment of inertia about the diameter will be the moment of inertia about the perpendicular axis, which is mr square. These diametrical axes are this center of mass axis. So ICOM multiplied by 2 times, because both of them, this diameter or this diameter passing through the center of mass, are the same. So ICOM is mr square by 2. I can now substitute it over here. Mr square by 2 plus mr square is the moment of inertia about the tangential axis. Hence, the answer to that is 3 by 2 mr square. Lot of people will mark this third option, which is absolutely wrong, because that r is radius. We have to give the answer in terms of diameter. So 2r is small r. Therefore, from here only you can see capital R is small r divided by 2. So resubstitute back this as small r divided by 2. That means by 4 if I square it, and 3 is there, by 2 is there, and m is also there. So r square replaced by r square by 4. Okay, So this will give me 3m small r square. 2 into 4 is 8. That is the final answer, 3 by 8. So see how tricky this question was. Option number 2 is correct. Many kids marked 3. They left it here. They forgot the diameter was given. Okay, clear? So it is not the third answer. It is the second answer. Yes. Arividya. Yes, perfect. Yes, definitely. What is the difference between green line and the blue line? Both please to center of mass. So both must be ICOM. No, both are ICOM, but the context of this ICOM over here is it is the diametrical axis. The context of this blue color ICOM that I'm talking about, there could be many center of mass axis, is specifically the diametrical axis. Okay, I hope that is clear. Sarvesh, cool? Yeah. And this axis, the green one, is the perpendicular axis. So also the center of mass axis, but I can't use ICOM label 3-4 times. It will be confusing. So I have given it its distinct name so that it is easy to understand when we are applying the theorem. Okay, great. Now that we have understood parallel perpendicular axis theorem, there are some combination problems also where you might have one body over here, another body over here, and maybe there is an axis like this, and you have to find what is the total moment of inertia, and the total moment of inertia will be just the moment of inertia of the first body plus the second body about that axis. Those kind of questions can come. I'll show you, don't worry. And the other kind of questions which come is the ones on cavity. So maybe some part is taken out. So there is a cavity over here. There is a cavity over here. So the moment of inertia, which is now net effective, will be the old moment of inertia minus the moment of inertia of the cavity which is taken out. So this kind of questions can also come. Okay, there could be some access given to you. So either the cavity questions where you're scooping out something or you're combining 2 or 3 bodies. Let's understand it via questions. Otherwise, it is theory. I mean, I1 plus I2 or I1 minus I cavity, it's nothing great. Okay, so let's start with some questions coming up on your screen. Here it is. The moment of inertia of some rod of some mass and length L about an axis passing through its center and normal to its length is alpha. Now the rod is cut into 2 equal parts and these parts are now joined symmetrically to form a cross shape. Moment of inertia about the cross about an axis through the center and normal to the plane is how much? Very crazy question. Yeah. Crazy boy. If there are kids out here who are having hope and are doing it in 2 months, you have 1.5 years. So if a student in 12th standard has not lost hope, how can you lose hope? You have more than a year. Okay, you don't have 1.5 years, you have 1 year, 2 months only. Okay, that is wrong to say 1.5 years because next year at this point of time, you will be barely 2 months away from the first attempt and you will be preparing for the practicals, pre-boards. That is another story. So, yes, it is possible. But if you keep asking that question, then it is not possible. You have to get that plan into action and execution. Okay, I have made a video on Can I Crack JEE 2027 on the channel. Please watch it. Yeah, JEE Advance is in June, but the preparation that you will get time wise is gone after first attempt because after first attempt boards, after boards second attempt, after second attempt you think you will get time for advance. What about other exams? BitSat is going to be there, and it's not like you will not give them. IIT exam, VIT all the other backup exams will also be there, state entrance exam. So that is going to eat away a lot of your time. Remember that. And exam fatigue also comes into play where you're just giving exam and your body mind just gives up after a point. So all these things matter. Okay, if otherwise it looks like 6 months, 2 months, 4 months. Going through those months is the task. Let's start. The first one, if you take a rod of length L and mass M, and this is length L, and the axis is this one. The moment of inertia is basically given to be alpha. Okay. Now the rod is cut into two equal parts. Okay, so let's cut it into two equal parts. Imagine one part like this and the other part like this. Now what will happen? The length will be L by 2 and L by 2, of course. Mass will be also M by 2 and M by 2. Now when you try to calculate the moment of inertia of these rods, how will it look like? Will it be still alpha? No. Think like this. This alpha is nothing but the mass into L square divided by 12. Mass has become half. Length has also become half. So the moment of inertia will become how many times less? Think logically, guys. Yeah, this will become half. Length also has become half. So this will become 2 square, which is 4. 4 2s are 8. So 1 by 8 times of ml square by 12. So it is alpha by 8, because this particular value, this ml square by 12 is basically alpha. Mass has become half, divides. Length also has become half. 2 square is 4. 2 into 4 is 8. In the denominator, 12 remains as it is. So ml square by 12 is your original moment of inertia. So it has become 8 times less, every single part of it. But that's not the end. You have now made it into a cross shape. Okay, so let's make a cross out of it. Let's make a cross out of it like this, maybe. All right. And then what you have done is you have taken the moment of inertia about this particular axis. This particular axis like this. See if you're able to visualize. So this new total moment of inertia will be the sum of moment of inertia. Because I just told you some time back, if there are two or more bodies, the total moment of inertia of the combined system is each moment of inertia being added. So use this combination property. So this guy's and this guy's moment of inertia is each alpha by 8. So alpha by 8 plus alpha by 8. Only two rods were there. Sorry, why did I say alpha by 2? Alpha by 8. So it is nothing but alpha by 4. So that is the answer, which is option number 2. Option number 2. Is that clear, everyone? Why it is alpha by 4? Option number 2. Sir, I'm writing various mock tests. I'm scoring around 210 on an average. Sir, will I get a seat in the top NIT? Srikant, if you're writing tests and getting 210, it's a very good score. Very good. Keep it up. But also, I'm not really sure which tests you are writing. So it also depends on which institute, how much errors, is it very easy or very difficult? Questions are equally scattered. Is it of same pattern types, model types, and weightage also? So it depends on that as well. So if you have been giving Vedantu tests, the Ekalavya test series especially, then I am pretty sure you are on the right track. You are going to get 99 percentile for sure if you maintain the same momentum. 99 is bare minimum that you should get. Now, if you progress over this, you can easily get 99.567 also. All right. Good evening, Dakshan. Yes, alpha by 4, Harish. Yeah, perfect. Yeah. Okay, perfect. Yeah, if it is Vedantu, like I said, I just gave the answer. All right. Now, let's do the exact reverse question where there is a cavity inside. So something has been scooped out. There is a disk, mass m, rotating perpendicular to its plane. A small circular part is removed. And now the question is moment of inertia of the remaining part of the original disk of that figure. Like I said, in such questions, whenever moment of inertia is asked, you take the total moment of inertia and subtract it from the cavity. So in this question also, the story remains the same. So the net moment of inertia about this particular axis. So the question is find the moment of inertia of the remaining part will be the moment of inertia of the original disk which was there. So there is that uniform disk of radius r and mass m, and from that you are going to take out a cavity. So moment of inertia of the cavity which is going to be taken off. A small circular part is being removed from the original disk. Okay, so that is how I'll first interpret the question. That is the first step. Next step, let's write down whatever I know and then we'll proceed. The moment of inertia of that entire disk, guys, this entire disk, imagine everything was there. Nothing is removed initially. If I rotate it about the center, the moment of inertia will be mass into r square divided by 2, of course. Okay, perfect. Now the problem is this guy. What is this cavity going to be? So let's think what is the moment of inertia of the cavity. A lot of people make mistakes over here. So let's be very, very careful. See, this is my cavity. This is my cavity which has to be removed. Okay, this is the cavity which has to be removed. Let's forget this for some time. The moment of inertia of this cavity about this axis has to be found in this manner. First, imagine if I know the moment of inertia about this point, which is basically the center of mass, I have to shift the center of mass by this much distance. And how much is that shift going to be? If this is r, this is going to be r divided by 2. So the moment of inertia of the cavity part about that same axis, you cannot choose different axis. Whatever axis I'm trying to find for the net one, the total one, the disk cavity one, everything should be same axis. So that is the common mistake which many kids make. So the same axis if I take, I have to shift the axis from center of mass to this point. This is the point where students make a mistake or do not understand it. Did you understand? So when I write this equation, each term is about the same axis. And who is my axis? This is my axis. This is my axis. So I need to be consistent throughout the problem. So the formula which I know for the cavity is the disk formula about the center. So I need to shift it. So I need to shift it by how much? Mass of the disk into r by 2 square. The problem is I don't even know the mass of the cavity. That's another headache. Oh, what to do? I know one thing. Mass per unit area will be same. So that is the concept which I will use. So the concept that I will use is the mass per unit area is going to be the same. Is going to be the same. So if you take the entire disk, if you take the entire disk, the mass was m, area was pi r square. If you just take the cavity part, the mass is small m and area is pi, radius is r by 2. Notice this is nothing but how much? R by 2. Is that clear? So that is basically r by 2 radius. So this will be pi r by 2 whole square. So from this, what do we get small m as? Capital M. Then this r by 2 square will go on the top. So r square by 4 divided by r square, which is m by 4. So m by 4, r square cancelled. So the cavity which has been removed has a mass of capital M, original mass by 4 times. Very good. Now put this over here. Using parallel axis theorem, ICOM plus mass which is being shifted into the shift square. This is parallel axis theorem. ICOM is m r by 2. The radius is r by 2 square divided by 2. A lot of students make a mistake here also. because they miss the radius of the small disk is not r, it is r by 2. So about the center of mass, it is mr by 2 square by 2. So that 2 is there because of the disk. This by 2 is there because of the radius. Plus m into shift. Shift is r by 2. So r by 2 whole square, which brings me to, see guys, this is 2 square, which is 4. 4 2s are 8. So it will become m r square divided by 8 plus this is going to be m capital R square divided by 4, which brings me to 1 by 8 plus 1 by 4. So if I multiply by 2 both times, so 8 will be common denominator. 2 plus 1 is 3. So 3 by 8 m r square, but I should not stop at that place. So 3 by 8, what is small m? It is capital M divided by 4, and this is r square. So this will become 3 m r square divided by 8 multiplied by 4, that is 32. So 3 m r square by 32 is the moment of inertia of the cavity being removed. So lot of chances are there of mistakes, right from the mass calculation to the shift calculation, or even substituting the radius. Lot of calculations, mistakes can happen in this problem. So that is why you should practice this question multiple times. It has come again and again. So substitute that. What is it? 3 mr square by 32. So 3 mr square divided by 32. Is that clear? Okay, now we can take the LCM, of course. LCM is 32. So this will go 16 times. So 16 mr square minus 3 mr square. 16 minus 3 is 13. So it will become 13 by 32 mr square, which is the fourth option. Yeah, perfect. That is the correct answer. Clear, guys? Yes, Malonan B. Yes, definitely, man. May is a good time to complete. Actually, May is little late. By April, you should have done. Do not take the target as May. Actually, you should keep it March end only, because April onwards you should move on to 12th standard syllabus. So worst case April, but ideally by March end, if your state board syllabus or CBSE board, whatever classes, term exams are there, maximum you can push it till April, not beyond April. Don't push it till May. May is too late. Yeah. All right. Machari, Dilip Kumar. Awesome. Very good. Okay. So that is the answer. Now, I have kept a homework question for all of you. I'm pretty sure you can solve this. Take a wire and you bring it into a semicircle. What is the moment of inertia of a line perpendicular to the plane of the wire passing through the center? A very simple question. Just try it out as homework. But post the answer. This is your homework. Post the answer in the comment section. Okay. Answer should be there in the comments. Next lecture, I'm going to open up the comments and I'm going to see who and all have answered. Yeah. I hope you guys enjoyed today's lecture, guys. Yeah. It was a brilliant session which we had. We studied every single concept of moment of inertia, what it is, what does it depend on, radius of gyration, different bodies moment of inertia along with some derivations including integration, then the axis theorems, perpendicular and parallel, and finally the combining and cavity problems. So it was a brilliant session, completely in detail. Next lecture we'll be doing torque and pulleys with masses and also balancing toppling questions, okay, before moving ahead, right? So have a great time and do not forget to like and comment the answer of the homework question below. Thank you for subscribing if you have not done that, and do not forget that the entire lecture PDF along with timestamps will automatically pop up after some time. I mean, the processing will happen. With AI will do it for you. So just click the link below over here, the PDF, smart notes, even practice questions will come up. Just click, and yes, it is absolutely free. You don't have to pay anything. The subscription charges were actually 200 rupees per month, but it has been completely waived off just for you guys, because we want to help you. Okay. and we launched this as our Children's Day offer. Yeah, so on the occasion of Children's Day, we have created this beautiful thing. Yes, you can even create quizzes and practice questions on today's class. Vedai is smart. Vedai will also give screenshots, timestamps, everything. Just use it and you will only realize. Okay. Thank you so much. Have a great time. Bye bye. Take care.